Hello students. Today we'll talk about say coordination isomerism, right? So our main focus will be on the isomerism part. So far we have covered up till the IUPAC nomenclature of mononuclear coordination compound. So this part we have covered. Okay. So today will be our main focus will be isomerism. Okay. So let's start our today's lecture. So if I look at the topics in more detail, then I would say that first we will see what is meant by isomerism in coordination compound. Then we will see its various types, starting from geometrical, optical, linkage, coordination, ionization, solvent, stereomerism, and some of the questions we will also see. So let us start our today's class with the concept of isomerism. So what are isomerism? So basically it is the property of, it is a phenomena, I would say, in which two of the species will have the same formula, molecular formula, but will have a different structure, I would say a different spatial arrangement. Spatial arrangement means in the space, in the 3D space, the position of their atoms with respect to their isomer varies, okay? Or with respect to the one which is having the same molecular formula will vary. Clear? Now, isomerism is the phenomena which I said right just now is property of not a single compound, but it is with respect to some other compound, and those set of compounds are called as isomers. So isomer are two or more compounds that have the same chemical formula, right? As I have told you, they have the same chemical formula but have a different arrangement of atoms. So we'll see the example so that we can get a more clear picture. Now, what is the effect of this different arrangement? So it impacts our physical properties and our both our chemical properties, right? Because all our physical and chemical properties are totally dependent upon structure. So once we are changing the structure, we are changing the properties. So if I talk about the two principal types of isomerism are known in coordination compound, that is geometrical and stereo. Okay. So we will see a table to get a more clear picture. So there are stereo and structure. Okay, sorry, stereo and structure, not stereo and geometrical. Stereo and structural. In stereo, we will have geometrical and optical, whereas in structural, we will have linkage, coordination, ionization, and solvent isomerism. So, what is the meaning of stereo? So, in the case of stereo, what are we doing? We are changing the position of the groups, right? Means the structure is same. The structure is completely same. What we are doing, we are just changing the position of the spatial arrangement or the spatial arrangement of the groups. But in structural isomerism, the linkage is also changed. I would say the structure is changed. Okay, suppose A was attached to B was attached to C. So it is possible in the structural other isomer that now A is attached to C and C is attached to B. Okay, means the bonding is changed in case of structural isomerism. But in stereoisomerism, bonding is same. Only the position of the group that is attached to that bond will change. Clear? Okay. So in stereoisomerism, we have geometrical and optical, as I said, and structural we have 4 types. Now, stereoisomers have the same chemical formula and chemical bonds also are same, but different spatial arrangement. Now, this is the table that you should look upon. So, if I talk about isomerism, so they can be broadly divided into two, stereo and structural. Now, further, structural can be divided into geometrical and optical. Yeah, whereas structural stereo can be divided into geometrical and optical, whereas structural can be divided into solvent, linkage, coordination, and ionization. So this structural is specific for only coordination compounds. Okay, so this classification, you can say a sort of it can be related to organic chemistry, but if I talk about the whole table, if I talk about the whole hierarchy, then I would say that it is totally about coordination compound, because we don't have any solvent isomerism in case of organic. Clear? Now, talking about geometrical isomerism, there are 2 types, cis and trans. Okay, cis and trans. Whereas in case of optical, we have D and L form, I would say, levorotatory and dextrorotatory, right? Whereas in case of structure, we have solvate, linkage, coordination, and ionization. So we will try to understand with the help of example all of this. Okay. Now let us move to our first type. That is our geometrical isomerism. Now this isomerism arises in heteroleptic complexes. So we have seen this term. Heteroleptic means each of the ligands are not same, and due to different geometrical arrangement, we have this geometrical isomerism. Now, if I talk about the example, the most obvious example is shown by our square planar complex. So suppose we have a square planar complex in this fashion, mx2 L2, where m is the metal, x is one of the ligand that is having 2 count, and L is one of the ligand that is also having 2 count. Now two structures are possible. In first structure, both of the x are on the same side and both of the L are on the same side. Okay. Whereas in the second case, both x are on the opposite side and both L are on the opposite side. So we'll see the actual structure. So this is the one. Okay. So suppose this is x, this is our x, and now L we have taken as NH3. So this is the example of geometrical isomerism. You can see very clearly that in this case it is called as cis, in which both of the Cl are on the same side. Okay. But in the next case, the NH3 is on the two different sides. Now I will tell you a very interesting fact why this isomerism is important. So if I talk about cisplatin and transplatin, so they both have very specific special type of specificity. Okay. So one of this is used in the treatment of cancer. Okay. So this one shows a anti towards this. I would say it is used in cancer treatment, right? Where the trans one has no use. Okay. So the importance of this structure or the geometrical isomerism or the spatial isomerism is very important. Just by changing the structure, you would change the behavior of this compound in our body. Okay. So by this fact, you can understand that how important the spatial arrangement is. So we have seen the geometrical isomerism in case of square planar complexes. Now we don't have any, say, if we have any other type of arrangement. So initially we have seen an example in which we have two same ligands and other two ligands are same. Okay, so we say that Ma2 and B2 will show two isomers, one cis and one trans. So this will be MA and BB. This is for cis and this is for trans. Now for any other type of arrangement, so if I take, suppose I am taking MA3B, okay, so this will not show any type of isomerism, right? So we have 3 A's and 1 B. Now you put B anywhere, right? You will get the same structure at last. Okay, so you just rotate it, you will get the structure. If you put this B here, then again just rotate it twice or rotate it one time or rotate this one twice, you will get the same structure. Okay. Or you talk about all four ligands are different, then also it will not show any isomerism, geometrical isomerism. Clear? So only square planar complexes of the type Ma2P2 will show our cis trans isomerism. Now, if I talk about tetrahedral, so tetrahedral have no geometrical isomerism. So you can take any ligand, it will never show geometrical isomerism. But our octahedral complexes can show geometrical isomerism. So we are just building up a table right now. Okay. So for a square planar, we are saying that only M, A2, B2 type of square planar complexes will show isomerism, cis and trans. Tetrahedral, tetrahedral. So when I'm saying all about all the structure, so we'll see in which case we have this structure, right? So you don't have to worry about it. So in tetrahedral, we do not have any geometrical isomerism. Talking about octahedral, we have some. So let us see an example. So for octahedral, we have the case of mx2l4. Okay, mx2l4. So we have two x's, okay, and four l's. So this is the case of cis, right? Or I would say, I place it here. Okay, so this is the case of 6, this isomerism. Now, if I place both x's on the opposite side, suppose I am placing it on the opposite side in this fashion. Okay, so this will give me the case for trans. So we can say that octahedral of the type I am replacing x with this A2, B4 will show geometrical isomerism. Now, if we have suppose multi-dentate ligand, so in that case also we will see the geometrical isomerism. What I am saying is that suppose we have an example of this. So we have bidentate ligand. Bidentate ligand can chelate through 2 points. So one point is this and one point is this. We can take the example of this one, that is NH2, CH2, CH3. Okay, so we can write NH2, CH2 and NH2. Okay, so one will be this. So there are two such ligands. LLR of two count, right? So we'll take two. So this is one case. Suppose I am taking NH3 here. So this will be termed as cis. Clear? Now we can have trans also. How will be trans? I'm just writing a shortcut for it. NH2, NH2, and this one. Here we can have NH2, NH2, and this one, and rest of the ligand. Suppose I am taking another ligand here in place of this, and suppose I am taking H2, so that you don't get confused. H2O. Okay, and this is also H2O. Is it clear? So in this way, we can have two geometrical isomerism. This and this one is trans. So we can say that ligand of the type M, I'm representing a bidentate ligand with LL, and B or A you can write. So this can have geometrical isomerism. Clear? So far we have seen square planar, tetrahedral, and octahedral. So square planar of the type MA2B2 will show the geometrical isomerism. Tetrahedral will never show geometrical isomerism. And octahedral of the type MA2 and MLL2A will show geometrical isomerism. Now, if I ask you that how many isomeric pairs, geometrical isomeric pairs, are possible for square planars, so what you will say? So if I'm telling that pairs, then you will say one pair is possible, right? Cis and trans. For a square planar, only one pair is possible. Okay, so this should be kept in mind. If the question is asking that tell me the number of pairs, then I would say that only one pair is possible. Now, if they're asking that write the number of geometrical isomers that are possible, then you will say that two geometrical isomers are possible, cis and trans. Clear? So in the similar fashion, you talk about shoes, you say a pair of shoes. You don't say we have two pair of shoes if you have two shoes, right? Clear? So in that way only I'm saying. But if you are talking that, okay, just count the number of say isomers, you will write it is 2. So this should be clear. Sometimes children make mistake, and if they didn't get the question the right way, they do make mistake. Now let us see an example of this. So you can see very clearly it is of the type Ma2B4. So this is A2 and 4 B's are there in the form of NH3. So this sits in which both Cl are on the same side, and this one is trans in which both Cl are on the opposite side. Clear? Okay. As I talked about this one, so this is an example of bidentate ligand. Okay, this is called a bidentate ligand. Why it is called a bidentate ligand or didentate ligand? You could also pronounce it as didentate, but in most places it is written as Bi. So it can chelate through 2 points. This NH2 and this NH2, they both can chelate. So it is just a way of representing it. It is called as ethylene diamine and it is abbreviated as En. So we have written in this fashion. En with two scissors. It is showing that it is joined through 2 points. So in case we have both En on the same side, we'll say it cis. And if both En are on the opposite side, we'll say it trans. I want to make a very clear point here that you cannot have such structure in which, suppose we have taken CO, you cannot say that the En, one of the En is supported here and one is present on the opposite side. So this is not possible. So this is very wrong. Okay, they can be on the adjacent side, but they cannot be on the opposite side. Clear? You cannot connect it in this way because there will be a lot of strain and this is not possible. Or I would say you cannot make an angle of 180 degree between these. So you can see that there is an angle of 180 degree. You cannot make this. Whereas in this case, if you see, the angle is very clearly 90 degree. Okay. If I draw it more properly, you will get it. So we have CO. One of this NH2 is here. And this one is joint. You can clearly see this angle is 90 degree. And here also, in this case, if it is on the upside, this is NH2, H2, and this is also 90 degree. Okay, you can just imagine it that suppose this is our plane. Okay, this is our plane, right? We have placed the ligand on the upside. Now, if I just hold it, if I just hold it, you can see that the angle between this tip and this corner is a 90 degree. But if you are just jointing this corner, okay, so if you are just this corner and this corner, then they will make an angle of 180 degree between this, right? Clear? So in this fashion, I would say that you cannot connect it on the 180 degree. Clear? Now, another type of geometrical isomerism occurs in octahedral of the entity of the type Ma3B3. Now, this is not cis-trans, this is called as facial and meridonial, right? This is called as facial and meridonial. How is it named? So let us see an example of it. So if three donors of the same ligand occupy an adjacent site, then we call it as octahedral. And it is called as a facial octahedral. Whereas if they are not on the same side, then we tell it as meridonial. So let us clear it with the help of example. So this image you must have seen. Now, if three of the NO2s are on the same side, they are making a face right here. Okay, they are making a face out of it. Whereas in this case, they are not making such face. Although they are cis, okay, you can see very clearly that they are cis, right? But, and this is also cis, but this is making a face, and this one is not making a face. What I'm saying, so look in this fashion. So suppose we have our C, NH3. What are the ligands? NO2. NO2. And this is also NO2. Whereas other are NH3, NH3, and NH3. So if you just join these three, it will make a triangle out of it. Okay? Clear? And all the NO2 will be on the vertices. right? But if you see these triangle, okay, if you see these triangle, it is not the case. Okay, clear? So this facial is called facial and this is called meritorial. Okay. So this is in this case also the three NO2 are on the vertices. Okay, so this is similar. But if you see that cobalt is not part of that triangle. Okay, the NO2 triangle which is being made by the three NO2s, this NO2, this NO2, and this NO2, cobalt is not a part. But in this case, the triangle which is made by the three NO2, cobalt is also a part of this. You can see it is present on the middle of the line. But in this case, this triangle has nothing to do with CO. So this is the difference. So in this way, you should imagine it, right? This is very important. So in the exam, you will not see the same type of arrangement and you will get confused. Just simply connect all the dots. And if you see that the triangle that is being formed also includes CO, then you will say that it is meridian. And if it is not including CO, then you will say that it is facial. Clear? Okay. Now let us move to another type, optical isomerism. So what is optical isomerism? So optical isomerism is basically the isomerism in which you see in case of cis, what we have cis and trans, we have seen that if you place both of this in this fashion, cis and trans, then they both are not uh, interconvertible, right? You have to break the bond, right? You are breaking the bond. Cis and trans are on the opposite side. Clear? While in case of optical isomerism, we have a case of image isomerism. Okay, image. So basically, what do we do? Say we have two structures. So both of them will be the image of each other. Okay, so if you place both of them on the same side, then this will be the image form of the other. Right? And one more type is there that is called as di-stereoisomerism. That is a different type. Clear? So in case of optical, we have the case of enantiomer. We call it as enantiomers, right? So in optical isomerism, what do we see? That non superimposable image is formed. So we'll see the example and get it more clear. So you can take the example of your hand. Your both hands are there. So if you place both of your hands, you will see that this one is forming the mirror image of this one. Okay, just place it like this. How you can imagine it? If you place your single hand on the mirror, you will see that the image of this hand is forming on the opposite side on the mirror, and you will find that it is similar to this hand, left hand. Okay, but if you just try to superimpose it, what is superimpose? Keep one hand on the other, you will see that it is not possible. Okay, so they are not just covering it. Just try to keep it. Okay, keep it in this fashion. They will not cover it whole. You can cover it in this way, but see, only one of the face is being superimposed on this. The other face is not properly covered. So you should place in such way that you can place top of each other. Okay, so it is not possible for this. Did you get my point? But in case, suppose you're taking the case of only one finger. Okay, so you're taking one finger. If you keep it in this fashion, whole of this will be covered. You can see a single finger from this side. Okay, see, you can see only single finger. But if you keep hands on each other, one of the hand is still visible. Right? So this is called superimposable. So if it is completely covering it, which is not the case of hand, it is called as superimposable, which is the case of finger. You can see that the one of the finger is completely covered. Okay, so you see like this in a ray, you can see that only one finger is seen, whereas we have one more finger, right? So this should be kept in mind. So this is called as superimposable. Clear? If you take this bottle, keep one more bottle play in front of this. This backward bottle cannot be visible. Okay. You can take a similar case for this pen. Okay. If you place a similar pen here, the this pen which is in the behind, it cannot be seen. So this is called as superimposable. Right? Did you get my point? What I'm trying to make? Okay. Now, the one which is not superimposable are called chiral. What are they called? They are called as chiral. And if both of these are mirror image, then this is the enantiomer of this. Okay, this is the enantiomer of this. Now, if two images are possible, then one of this will rotate the right to left. And one of this will rotate the right to right. So what is the meaning of this? So what do we do? Suppose we have two molecules which are non-superimposable, right? So we take the mirror image, we take one molecule, place it on a mirror, we got another mirror, we got another image, and now both of these images are not superimposable. Then next step, what do? We take two beakers. In one beaker, we take one of the compound, and in the other beaker, we take the mirror image compound. Okay, just make a solution out of it and pass plain polarized light through both of them. Okay, plain polarized light, basically it is a type of light which is having the propagation only in one direction. Okay, so they are called plain polarized light, PPL. Now, if you just pass through both of this solution, you will see. So, suppose this is a beaker solution. Okay, so suppose this is a beaker solution, right? Now, your light is coming. If the light goes in this way, okay. So, if you see in this perspective, if it is going right, okay. Suppose it is coming and it comes and rotate right. Okay. So if it goes right, then we call it as dextrorotatory, and it goes left, then we call it as levorotatory. Clear? Next. So you can see a very clear example of it. Okay, so this is called as dextro and levo. Why it is calling as dextro and levo? How will identify it? So if I ask you, how will identify it? You can't place a mirror each time and see that whether it is superimposable or not. You will need a lot of imagination and time. And in exam, you don't have much time. So for that, simply locate a plane that is called as plane of symmetry. So what is plane of symmetry basically? So it is a plane. So if you put that plane like this between the molecule and both of the side are same, then we call it as, okay, this is having a plane of symmetry and it will not show optical isomerism. What is the example of that? Suppose we take this M, two ligands are there, right? This is a transform. You must have seen this. Now, if you place suppose a partition here, right? You place a partition here. This B molecules is splitting in two parts. Similarly, there is A present on the adjacent side. We have A. Here is A and here is A. You can see that both of this are having the same type of arrangement. On the left side, we have same thing. If you go on the right side in the same direction, you will have the same thing. Similarly, in the here. Okay, and these three molecule items are bifurcated. They are falling in the plane of symmetry. Now we can say that, okay, this will not show geometrical isomerism, right? This will not show geometrical isomerism. Whereas if you take the case of this one, let me draw this example here. PT, okay, ethylene diamide. I'm just drawing it properly, expanding the structure of ethylene diamide. Looks like this. Okay, so we have NH2, two CH2s, and this is on the same adjacent side. It is NH2, CH2, and we are having what? Cl here. Now, if I try to draw a plane of symmetry, then you will see that it is not possible to have one. Suppose you are passing the plane of symmetry on the plane. So suppose this is your octahedral complex. Okay, this is your octahedral complex. One of the ligand is on the upside, one is on the downside. Okay. Now what I am doing, I am passing the plane of symmetry in this fashion. Just co-planar with the plane on which the four ligands are present. We are passing the plane like this. So if you cut it in this fashion, and all of the ligands will be cut. So which the molecules which are falling within the plane of symmetry, you don't have to look for them. The one which is not falling is this Cl, that is this Cl and this NH2. Now you can see very clearly that on the upper side we have Cl, whereas the downside we have NH2. So this is not having a plane of symmetry. We can try another plane. Suppose we are trying another plane, right? What do? We can try another plane. That plane would be, we just erase it. Okay. So this is our structure. Now the second plane, what I'm trying to do, this was our octahedron. One ligand was up, one ligand was down. I'm just trying to cut it from the middle such that both of the ligands up and down fall on this plane. Okay, so I'm cutting it from here. If I just cut it like this, let me draw it with a dotted one to show you. So once I cut in this fashion, on the left hand side we have NH2, where on the right hand side we have Cl. Okay, so this is not. Similarly, on the left hand side we have NH2, on the right hand side we have NH2, but we don't have this thing. Okay, so you should see each and every structure. So we don't have this one, right? So it was failed in the first part only, where we have NH2 here and no NH2 on this side. So this is not having a plane of symmetry. You can think of another plane, just try to cut it from different sides. You will always see that they both will never be superimposable. Okay, just try this exercise at home. It is very useful. So once you get used to it, you will not need to learn that okay, this is this and this will show dextro, this will show isomerism, this will not show isomerism. You don't need to learn them. Once you are able to recognize them or imagine them, you will not have a necessity to learn them. Clear? Now I would say one more thing, that only cis isomerism will show geometrical isomerism. If you just draw the trans of it, you will not observe a say optical isomerism. So suppose I am drawing the trans one, right? So what will be the trans one? We have PT, NH2, two carbons, NH2. Here also NH2, PT and this. So we have Cl here and we have Cl here. So this is the transform. Okay. So what I will do, I will just pass a plane of symmetry that is parallel to the 4 ligand. So similarly, we are passing it like this. Okay. So co-planar with this. Okay. So passing it like this. So we cut all the molecules. So as I said, the one which is falling in the plane, you don't have to worry about it. The left out one is which one? This Cl is left out and this Cl is left out. Now you can see very clearly that there is one Cl and one Cl. Okay, so we have mirror image. Do we have any other component that is attached to PT which is not falling in the plane of symmetry? So no other component are there. This NH2, NH2, these all are falling in the plane of symmetry, so you don't have to worry about it. See, the plane which you are passing, if the molecule is in that plane, you don't have to worry about it. If it is falling out of the plane, you will see that whether there is a mirror image that is present down or not. So there is a mirror image. This will not show optical isomerism. Okay. Is it clear? Okay. Now you don't have to also learn that whether it is dextro or levo. This is not important. You know, if you know it, if you remember it, well and good for information. But you don't need to learn it that this is dextro and this is levo. Clear? Now let us move to structural isomerisms. Okay, what is the structural isomerism? The first one is called as linkage isomerism. Okay, so the term linkage will define this isomerism, right? So suppose we have ambident, we have the example of ambident ligands. So due to ambident ligand, we have the case of linkage isomerism. So if there is a linkage or isomerism, then and then only we will have to see a if and if there is a immediate ligand, then only we can see the linkage isomerism. So we can see an example of it. If we have NCS, suppose, then the metal can say chelate with the N part and with the S part. Both are possible. If I just draw the structure, I've drawn it earlier, also I'm drawing it again. Okay, so this is possible. Now in this case, N will chelate, and if S is there, basically SCN, right? SCN. So three bonds are formed and with a negative sign. So in this case, S will chelate. So whenever there is a mident ligand, there is always a chance of linkage isomerism. Is it clear? Okay. Now NO2 can also have two sides, right? NO2 can also have two sides, which can be ONO and from nitrogen side. So it can chelate through N and oxygen both. Clear? So if I ask you for this compound, what is the number of linkage isomers that are possible? Linkage isomers that are possible. So we would say two isomers. So in first case, the CO will be attached directly with the N, and in the second case, CO will be attached directly to the O of the NO2. So two structures are possible. So this was recognized, this linkage isomerism was recognized by Jorgensen, in which we obtained as red form. In the red form, the ONO structure was there, means oxygen was chelating. Whereas in yellow form, N was chelating. Clear? What happens in this type of isomerism? The next is called as coordination isomerism. So in this isomerism, what happens is ligand changes, right? What happens? Ligand changes. Suppose we have an example of this. So it is not an example of mononuclear, but a dinuclear complex in which we have two metals present. Okay, so we don't have to worry about it. So what are we interested in is that the ligand are interchanging. So initially, all of the NH3 are chelated to Cr, and all of the CNs are chelated to CO. Now, what will happen? So in this isomerism, suppose one of the CN goes and chelate to Cr, and one of the NH3 goes and chelate to CO. So in that case, we can have the case of coordination isomerism. Okay, clear? So you can have a more example for a mononuclear also. Let us focus on mononuclear. So suppose we have one Br outside. So now this Br can go inside and SO4 can come outside. So this going outside and coming outside is simply change of valency from primary to secondary. So what are we doing? We're changing valencies. Okay, clear? So if I ask you that suppose one Br was present and one more Cl is present. Okay, so what are the possibilities that one Br will go? Okay, one Cl can go, right? So there will be multiple possibilities. Clear? So if you are asked that, okay, just tell this that whether this will show ionization isomerism or not, you will only see that if there is a ligand that is present outside the coordination sphere, you can see that Br is present. Similarly, in this case, outside this coordination sphere, this Cn is there. Clear? Next is solvate isomerism. Now, this solvate isomerism, how does it arises? So it basically arises due to H2. It is very clear from the solvate word. So what do? We hydrate it, right? So for example, we have this. Okay, we have this. Next, so this bracket will be here, not here. Okay. Now what happens is this form a crystal. Okay, so this is forming dot H2. You must have seen this type of thing, that in case of suppose we have a baking soda dot 10H2O. Okay, so that is the form of crystal. So this can have hydrate, this can show solvate isomerism. Now, if I look at the types, so what are the types of stereoisomers that are possible for different type of formulas? So what I've done, I've tried to generalize it. So I'm passing it quick. So let us look at some of the examples. Okay, so you will get a clear picture how you are able to do in the exam. Now, suppose I am taking the example of Ma4B2. Okay, Ma4B2. right? Now, if I ask you, what are the possibilities of stereoisomers? Okay, so two stereoisomers will be possible, cis and trans. Now, in case of MA5B, only one is possible. You cannot have any other type of structure. Similarly, for MA6, one. MA3B3, again, two are possible. And MA4BC, two are possible. So if I ask you, just draw the cis trans of this MA4BC, how this are, how you will do? So what I say, so we have this kind of structure MA4BC. So we can have one such structure. A's are here, B and C. So in this case, both B and C are on the opposite side, right? So this will be termed as trans. Now if I draw one more structure such that B and C are on the same side, that is, they're making an angle of 90 degree. In this case, they're making an angle of 180 degree. So A and A. So this will be termed as this. Clear? Got my point? Okay. So if I try to ask you what MH3B3, just try to draw it by yourself again, right? We can have many examples in such way. Okay, limited examples are possible. Suppose we have MA3BCD, right? Then we can have 5 stereoisomers. Okay, and one enantiomeric pair. Similarly, for MA2BCD, 15 and 6. Okay, just try to draw each of this. You will get more and more informative once you draw it. I have more examples. Okay, MABC hold twice. So let us try this. So what is the meaning of this? This means that this is a bidentate ligand having two different donor sites, right? Now, and what is the meaning of this? This is a bidentate ligand but having the same donor site. Okay, so this is the meaning of this, right? So if I ask you, what other types of enantiomeric pairs are there? So let's try to draw it by yourself. Okay. Similarly, for MAB3, we can have 2. How it is 2? So the donation sites are different. I'm saying the donation sites are different. MAB3. Okay, so 3 are there. Now, if you try to draw a plane of symmetry, you will not find a plane of symmetry. Okay, you will never find a plane of symmetry. So, if you draw a mirror image of this, then they both will not be superimposable to each other. That will result in one pair of isomers. This is one pair. Can we have more examples? Yes, we can have more type structure. So what we do, this is AB. Now, in this case, if you see, A and A are here. So what I'm doing, I'm placing it in this fashion. Okay. A, B. Okay. So all are being opposite. A, B, A, B, A, B. In this case, we have A, B, A, B, B. Now, if you again just try to draw a plane of symmetry, you will not find anyone. Just try to draw it by itself. So this will result in another enantiomeric pair. Clear? Now let us solve some questions. So in this, we have to indicate the type of isomerism that is exhibited by each of this. We just have to indicate the type of isomerism it can show. Clear? Let us start to draw to see which type of isomerism can it show. So first we will see, say stereoisomers, right? So can it show a stereoisomer? So this is basically a square planar complex. Okay. So this will clearly show cis trans isomerism. First of all, geometrical. Can it show any type of isomerism? Does it have any ambident ligand? No. No ambident ligands are present. Second thing, are there any counter anions present outside the coordination sphere? No. So it can neither show this, say our linkage isomerism, and nor it can show the coordination isomerism. Clear? So it can only show geometrical isomerism. Talking about ethylene diamine, just try to draw it. Okay, so if you have ethylene diamine, so there can be three. Let me draw the structure of ethylene diamine. So it will be in this fashion: O, C, O. So I am just drawing the chelating ligand, not the middle one, and this way. Okay, clear? Now if I try to draw a plane of symmetry across this, you will not find one. Okay, so they can show optical isomerism. Only optical isomerism it can show. This can show geometrical isomerism. What about this? So this has ambident ligand, right? Plus this has a counter ion outside of this. Clear? Okay, if you see the second example, there is also a counter ion. So it can also show coordination isomerism. Now this one, if I talk about this one, so this can show first of all coordination in the first side. Next, it can show ambident one. Why? Because NO2 has a ambident, so it can show linkage isomerism. Clear? Now, what are the next types that can be possible? Here in the first example, we can have hydrate also because it has H2O. Can it show geometrical isomerism? So let us draw it. So 5 NH3s are there and 1 NO2. So we have seen in the table that it cannot show. So geometrical is not possible. Is optical possible? Okay, so let us think about it. So can it show optical? No, it cannot show optical. Okay, so let us draw the structure, right? Just draw the structure. We have 5 NH3s and 1 NO2. Okay, 5 NH3s and 1 NO2. To draw a plane of symmetry, no plane of symmetry. Can you draw it here? No. Okay, so it will also show optical isomerism. Plus, since this has a hydrate, this one can show optical isomerism. Now talking about the last one, so it has two CLs and one, so it is of the type MAB and BC2. I would say C2. So geometrical isomerism, first of all, it is possible. I would say one more very important thing, that square planar complexes will never show optical isomerism. The reason behind it is that it is planar in nature. So all the compounds or all the structures which are planar in nature will never show optical isomerism. How? Suppose we take a mobile. Okay, so this is an example of planar. Okay, so when we pass a plane, all the molecules are cut in equal half on the both sides. Clear? So once we get a planar molecule, it will never show an optical isomerism. The first criteria is fulfilled. Talking about geometrical, it can show geometrical. Plus, it can show hydrate because it has water. Clear? So let us see the solution right now. So geometrical is possible. Clear? Optical is also possible. For the first one, this optical and geometrical. In this case, optical is possible. Again, optical is possible. Right? For this case, NO2, we have linkage plus we have ionization isomerism. Right? We can have optical isomerism and we can have geometrical also. And for the last case, it can only show geometrical isomerism. Clear? So just try to this question by yourself. So you have given the evidence, this and this are ionization isomerism. So how I will prove it? Clear? So this was for today's class. With this, I would end my lecture. Thank you.